So let's just look at a couple of examples without going into too many details about the predictability that is related to tropical stratosphere-troposphere coupling. The chapter goes into details about how to improve model representation of the stratosphere, which is necessary for capturing all these processes, and predictability that can be exploited from accurate representation of the processes, and the data needed and how data can be used to improve the models and process understanding. There is always the idea of improving process understanding, which can be translated to predictive understanding. So data that improves process understanding is always critical, and so on. I'm going to not include some of those details here, just to give you a sense of what is possible by focusing on predictable signals arising from tropical stratospheric tropospheric coupling. Okay, so this is an example from the book showing bivariate correlation skill for the ensemble mean real-time multivariate MJO index, which is we have looked at before, RMM. Predicted by the Bureau of Meteorology, which by the way doesn't have a good stratospheric representation and is yet able to show some strong dependence of skill on stratospheric processes like the QBO. This is showing as a function of lead time during the eastward QBO in blue and westward QBO in red. So westerly is coming down and easterly is coming down, as you saw before. For reference, the statistical forecast based on vector autoregression is also shown by dotted lines here. So you can see that those skills are not bad out to about a couple of pentads, so that has to be kept as a reference, which you must do better than that if you are doing dynamical forecasting, right? That's the goal. Only MJO events that have initial amplitudes of 1.2 to 1.7 at the time are considered over the period of 1981 to 2010. So this is basically the, if you remember the RMM diagram, the phase diagram with all the phases, there was an inner circle where the amplitude is less than 1, which are weak MJOs, and the signal to noise there is very small. So you pick MJOs that are outside the circle and are strong enough, and the signal to noise is strong enough, so that the teleconnections that you want to capture from MJO prediction are strong enough. Okay, so this is by bivariate correlation, and you can see that the easterly QBO phase has systematically higher bivariate correlation as a skill measure out to all pentads, so up to 40 days, whereas the westerly QBO has systematically lower skill in terms of bivariate correlation in the westerly phase of the QBO. Okay, so this is the statistical forecast, which shows similar behavior. So even the statistical properties used in this vector autoregression are capturing this relation to QBO. Again, the thing to remember is that BOM apparently doesn't have a good stratospheric representation. So the question is, if it does, if it adds, let's say, a better stratospheric resolution in the model, will it improve the forecast skill? This turns out to be not always the case, so one has to be careful. Anyway, jumping back to the polar vortex, there are processes like the sudden stratospheric warming, which are also related to upward wave propagation from the troposphere and wave breaking. And this is an example from disruption of the stratospheric polar vortex in early January 2021. This is showing in December 26, 2020, just after Santa Claus came back from delivering all the presents. Polar vortex is in good, solid, coherent shape, and then by January 5th, the first day of sudden stratospheric warming happens. What does it mean? Basically, when the polar vortex is perturbed this way and is broken into pieces this way, there is a reversal of winds in the middle, which you can see here. This is on January 15, where there's a much bigger break off of the polar vortex. Looking at the zonal mean winds in this blue, you can see here that you are beginning to perturb the winds and make them weaker, but then make them even easterlies and then oscillate around that. So a strong westerly polar vortex is going to have suddenly in the middle easterlies, and associated with that there is a very strong warming of let's see here, it's going from about 215 Kelvin to almost 240. So sometimes the warming can be as high as 70 Kelvin in just a few days. So you can see that this is very much in the sub-seasonal time scale. So why do we care about sudden stratospheric warming? Well, the process is apparently happens about 6 times in a decade, so it's not very often, but still it is something that has signatures at the S2S time scales and has predictability because of these polar because of the stratospheric tropospheric coupling processes that we know a little bit. But this sudden stratospheric warming has surface temperature anomalies which are quite significant, and you can see that average surface temperature anomaly over the January 5th to 23rd period, and this is a composite following all events over the study period. And clearly you can have significant warming and cooling signatures which can have surface weather manifestations in addition to perturbing the Arctic ice, sea ice, which can then cascade into other predictable signals and so on. So obviously this is very much relevant to tropospheric weather processes or extended range processes at S2S timescales that we are interested in. So this is showing the same thing, zonal mean zonal wind at 60 north and 10 hectopascal, and you can see the standard deviation is high, but there are many times where the zonal wind can go from the mean westerly positive numbers into easterlies when the perturbation of the polar vortex is very severe. Okay, that's what causes the sudden stratospheric warming. Okay, this is in the southern hemisphere at 60 south. The SSW is not that strong here. You can see that the variability is much smaller if you look in their spring and summer. So obviously this is the season, November to March or so, whereas here it should be from whatever April to October or so. You can see that the standard deviation or the variance is much smaller. So that asymmetry in the dynamics of the stratosphere and troposphere are very different hemispherically. To come back to the tropics, this is the study, a report from US CLIVAR. This is showing the fraction of 1 to 96 day variability in the 250 hectopascal geopotential height anomalies that is associated with the MJO. According to cross-spectral analysis, global fields are shown for the upper center, all boreal winters regardless of the QBO phase here. Bottom left is for the westerly QBO phase. We saw that the predictability was, prediction skill was lower in this phase, was much higher in this phase. So obviously the impact of easterly phase of the QBO on the 250 hectopascal geopotential height variance in the S2S band is quite strong, and this has to have an impact on predictability, as we saw. And just to close out the ideas, here it is again showing the bivariate correlation for all MJOs from various models, just to re-emphasize the points, including the BOM model that we already looked at, and in the easterly phase and in the westerly phase. And in general you can see that the drop-off of the correlation is much steeper here by about 4, some drop off by 2 to 3 pentads, some go up to 5 to 6 pentads, but these, most of them go beyond 4 or even up to 8 pentads, depending on which model you look at. So obviously a very good example of the QBO impact on the tropical S2S timescale prediction skill. Okay, this is showing the annular mode, which is another strong mode of variability in both hemispheres. There is a southern annular mode and the northern annular mode. In general, it appears that stratospheric radiation perturbations tend to project onto these so-called annular modes, which have this wavy pattern all the way down to the surface. So you can see that these signatures from the stratosphere down all the way to the surface are clearly seen here, and you can see the more wavy pattern here. Southern annular mode in general is more wavy because of the, again, the Southern Ocean configuration being more channel-like. This is the northern annular mode time scale. So this is the standard deviation, and these are the time scales. And you can see that definitely there are lower frequencies, but the standard deviation in the northern and southern hemisphere annular modes and the estimated decorrelation scale that is shown here. Okay, so that's seasonal time scale here, and the physics of these annular modes and their impact on the lower troposphere and their impact on the various S2S timescale processes like blocking. There is El Nino impacts going back up, there are MJO impacts going back up, and so on. So there is the whole spectrum of S2S processes from the deep tropics to the mid latitudes and all the way into the Arctic Circle, even in the sea ice and so on. So main point I would leave with in this section is that stratospheric tropospheric coupling offer many opportunities for S2S predictions. There are clear predictability processes that extend predictability timescales in the S2S band that we have been focusing on in this course. Okay.